Hello, everyone. Recently, when I was poking around on the internet, an ad popped up challenging me to solve this equation. While I did not click on the ad, I did make note of the equation because it had an appealing kind of form. I want to share with you now how I went about solving it, and for your enjoyment. Now, you may want to pause and take a moment to play with this equation yourself and look to solve for alpha. And when you're ready to do so, return to this video and we can compare notes, or you can compare notes. So let's begin by first taking a look at what this equation looks like just numerically. So here again is the equation: 25 raised to the power alpha minus 16 raised to the power alpha. And that difference is equal to 20 raised to the power alpha. So the question then is, what value of alpha makes this equation hold? Now, if we just experiment with some ready numbers, for example, if alpha is 1, we simply get 25 minus 16, that's equal to 9. Compare it to 20 raised to the power of 1, that's 20. Well, those certainly aren't equal. If we try 2, then we're going to get 25 squared is 625, 16 squared is 256. That differential is 369, which is not too far off from 20 squared, which is 400. So if we look at 3, if we think about alpha having a value of 3, we find that the mass of 25, that exponential growth applied to that mass, begins to really outpace everything else that's going on the board. And so now you can see this differential becomes quite a bit larger than 20 raised to the power 3. And if we moved even further, raise alpha or set alpha equal to 4, then again, the exponential growth applied to that larger mass of 25 really outpaces everything else. And now that differential is more than double the right-hand side of this equation. So it's fairly apparent from just looking at these trends that the as alpha gets larger and larger, the left-hand side of the equation is going to grow much more quickly than the right-hand side. And although I don't show it here, the same is true if we experiment with values of alpha less than 1 or values of alpha that are negative. We get the reverse, that the left-hand side implodes much more quickly than the right-hand side. And so the right-hand side is larger. And so essentially we have a monotonic trend where looks like that crossing point is somewhere just above 2. So just looking at this numerically, it suggests that the value of alpha that satisfies this equation, first of all, it looks like there will be a unique value that satisfies the equation, and that unique value will be something greater than 2, closer to 2, greater than 2, but closer to 2 than to 3. And indeed, we'll see that that's the case. And now one could continue this process numerically, and if one wants to solve for the value of alpha to 2 digits or 4 digits or whatever level of accuracy one is looking for, one could simply do that by repeating what I've done here using integer intervals and instead using decimal point interviews and quickly honing in on it. And that's a viable way to get a numerical estimate for the solution of this equation. I think it's more fun and more elegant to look for an analytical solution. It has a greater sort of purity and yields more satisfaction aesthetically somehow. So let's do that. So again, we start with this equation that we observe off the bat that the numbers, the integers 5 and 4 figure into this very readily. 25 is 5 squared, 16 is 4 squared, 20 is 5 times 4. So we can re-express this original equation in terms of 5s and 4s. And noting that 5 squared raised to the power alpha is the same as 5 raised to the power alpha squared. Likewise here, we can re-express the original equation now in terms of 5 raised to the power alpha and 4 raised to the power alpha. We can do a substitution here. Let's define a new variable x to be equal to 5 raised to the alpha, and likewise a new variable y to be 4 raised to the power alpha. So this equation now can re-expressed in terms of these x and y's that we've just introduced has a nice kind of simple form. X squared minus y squared equals x times y. And we can rearrange terms a little bit, put everything on the left-hand side. And so what we get is x squared minus yx minus y squared is equal to 0. Now, that term is in fact, you can see it's a quadratic equation in x and y. And to see that even more clearly and to sort of aid us in getting the solution, let's introduce some additional components here. Let A be 1, B minus y, and C minus y squared, which given the above is also going to be equal to minus b squared. So if we make this substitution, then we can take this equation, this quadratic equation, and re-express it in terms of that sort of iconic standardized form of the quadratic equation, ax squared plus bx plus c equals 0. And as we all know, the roots to that quadratic equation are expressed as x equals minus b plus or minus square root of b squared minus 4ac, and all of that over 2a. So that's the quadratic formula that we all probably were first exposed to in high school. And it continues to be a very handy tool. So that's allowing us to solve for x. Now, it's allowing us to solve for x, but it's solve for x in terms of these 3 sort of variables, a, b, and c. But remember that a is 1 and c is minus b squared. So we can substitute again up into this quadratic formula. And now we're expressing the solution x solely in terms of b, the variable b. So that's x is equal to minus b plus or minus square root of b squared plus 4b squared all over 2. Well, that expression inside the radical is simply 5b squared. And if we take the square root of 5b squared, that just gives us the square root of 5 times b. And so we can pull all of that out, simplify terms, group them, and now we have that x is just b minus b times this expression, which is just some numerical value, which is in fact this 1 plus or minus square root of 5 divided by 2. So we're almost there now. So now we have x is minus b times theta. So now we can start substituting back to the elements of the original equation, because that's what we want to do. Remember, we want to solve for alpha. So we have now that 5 raised to the power alpha is just equal to 4 raised to the power alpha times theta. And that if we divide both sides by 4 raised to the power alpha, that gives us on the left-hand side 5/4 or 1.25 raised to the power alpha, and that's equal to theta. We take the log of both sides then, and that gives us that alpha times the log of 1.25 is equal to the log of theta. Now, because we're taking the log of theta, that means that theta has to be a positive value. And so we'll see where that comes in just a moment. So now this tells us that alpha is simply log of theta divided by log of 1.25. So here we go. So theta, remember, is positive because we're taking the log, and you can only take log of a positive number. And so we get 1 plus square root of 5, because if we had looked at the other alternative root, 1 minus square root of 5, this would have been negative, and hence we couldn't take the log of it. So here we have the expression solving for alpha, the log of 1 plus square root of 5, all divided by 2, is 0.48. And that's divided by log of 1.25, which is 0.22. And you grind that out, and it's 2.16. Hooray, we've done it. Now, the only thing remaining then is to check and make sure that indeed what we've done is correct. And so hop back onto our spreadsheet. I'm expressing here alpha to more digits. It goes on many, many, many digits. And so what we get on the left-hand side of that original equation, when alpha is equal to this value, gives us 639.27, which is equal to 20 raised to that same power. And there we have it, QED. Hope you enjoyed it. See you next time.